see decimal conversion, efficient decimal conversion, 4 digits. And here, if you watch my previous video, I did this one, this part 3. This is similar to the part 3. What we have to do is we have to do the exact same thing. We have to do the conversion to the BCD, but here we have to do it for 4 digits. Each digit represents 4 bits, so that's why we are dealing with 16 bits. In the previous one we just did with 8 bits. Okay, now let's see how to do that. This is the one we have to adjust in order to make this happen. Here what has to happen is when we successfully run this code, it should be printing out these values for the BCD we have. Okay, now let's see what is the adjustment we need to make. And also, when we run this one, you have to make sure you set this serial receiver to be 125,000 baud rate, then only this will work. Currently if I run this one, it just print us equal. Okay, this is the one we are converting into by BCD. So this is the one we are converting into BCD. Therefore, after the equal sign, we have to get these numbers. The conversions are already there provided. We have to just get this number after this. In order to make this happen, we have to deal with this one given. This is the adjustment has to be done. We have to follow these instructions and complete this one. Let's go ahead and make it happen. Okay, let's do one by one. So here it's mentioned work and BCD are 16 bits. Okay, so extend operations appropriately. So 16 bits means we can use ACCD because ACCD is a 16 bits. ACCA and ACCB are like 8 bits, but in order to deal with the 16 bits we need to use ACCD, but we can also use 8 bits as well, because if you look at this one, serial hex 2, that is 8 bits, and we are gonna use this one in some location, but when we use this one, it's gonna only deal with A. So for that part we have to deal with only 8 bits, so we have to use accumulator A most of the time. Okay, now let's start this one. So serial deck 2, the title name is already there. Now let's go ahead and play with this. So inside this one they mentioned that store ACCD, the input to work. So let's do that. STD for the storing process, storing the accumulator D, and we are going to store work. And once you're done that, then here we have to do the clear statement as well. Clear BCD +1. This one will clear the high byte of the BCD. To clear the high byte, we have to put a BCD +1. And clear the low byte, I just put BCD. Okay, so this one done. It look better. Doesn't matter what spacing, and this is not necessary unless you're commenting. I just leave it one tab away so everything looks clean. Okay, and this one, if you look on my previous one, compare that one as well, so it makes a lot of sense. Okay, in the previous one we just deal with 2 digits, and here we stored with the STAA work, because this is just 8 bits, because each of the binary coded decimal only represents 4 bits at a time. 4 bits, each digits are 4 bits, so 2 digits only 8 bits, so we can just do everything with STA, that's accumulator A. But here we are dealing with 4 digits of binary coded decimal, that is 16 bits, so that's why we need to use the accumulator D, and others remain the same. And here we use clear BCD only once because we don't have a upper byte. 1 byte is 8 bits, so when we are dealing with the STD, that is 2 byte because 16 bits. So if it's 1 byte, this is enough, but when we are dealing with 2 byte, we have to deal with the upper byte and the lower byte as well. That's, if I start commenting, that will look better. So the first one, we are storing the 16-bit input value to work. And this one, clear the high byte of BCD variable. Okay, and this one, clear the low byte of BCD. Okay, so that has to be done here. And then if you compare here, we are loading X with 8 because this is just 8-bit, but here we are dealing with 16-bit, so I have to load X with 16 in this case. Loading X with 16 because load X, because it has to run 16 times. We are going to create a loop that has to run 16 times. So load the X register with the 16 for the loop counter. Okay, and then we are gonna have the loop, same thing here as well. You can name the loop anything you want. So I'm naming this one as loop, and I'm making sure I don't have the same name before, so it's not anywhere else, so that's good. I can name it as no loop. And then if you look at this one, I have STAA work. Okay, that's one we did before STD, and I'm looking at the loop right now, and here we have logical left shift, and that is shifting work. This one is good for the when you are dealing with accumulator A, but when you are dealing with accumulator E, it has to be done a little bit different. Okay, also let's read the instruction also before we go do it fully. So work 16 bits, so extend approximately, store ACCD to the input to work, clear BCD, we did it already, and then set up a loop, run 16 times using index, we did it, and then logical shift left work 16 bits, and 15-bit goes into carry, load BCD, add with carry to itself, EAA store to BCD, and 16 bits use 8-bit operations, finish loop, print out MSB of BCD values first using serial hex 2, and then LSB of BCD values. So first I'm loading the work. Need to load the work here. LDD work. And here what I'm doing is load the value from work. the accumulator. Okay, and then add work. And what does this gonna do is add the value in the digit register, the accumulator D, to itself, and then std work. This gonna store the result back to work. Okay, so here what you are doing, loading the work, adding work again to itself, and then storing whatever the new value we get with the work. And then now we had to do this like times has to be done. To store loops 16 times. Using X logical left shift work goes to dot BC with carry to itself. DAA stored to BCD but 8-bit operations. Use 8-bit operations. Okay. So here we have to use 8-bit operations, so we have to do 4-bit at a time. Like if you are using 8-bit operation, we have to do it twice. Let's look at the previous one. Here this is just 8-bit, so doing once was enough, but here we had to do the exact same thing 2 times. Okay, and here if you look at the first, we are shifting. Logical left shift, and then we are loading a accumulator A to the BCD, and then we are dealing with the carry ADCA BCD. This is add carry to with itself, and then after the adding process to convert into BCD, because when we are adding it's gonna be hexadecimal. To convert this one into BCD, we have to use EAA, that is decimal adjust accumulator A. That will turn anything above 9 into, like for example, if you get above 9, that becomes A in hexadecimal. But in BCD the maximum range is 0 to 9, but it's 16 bits, but it's in 0 to 9 range. I mean each letter is 1 byte, 4 bits, like hexadecimal, but when you're adding, it should be only within the 0 to 9 range. So to do the adjustment, the DAA at 6 for anything that's above 9, and make it to between the 0 to 9 range. Okay, and then store it in the BCD, and then DEX is to complete the loop, and BNE, this loop exists when the branch is equal to 0. Branch not equal to 0 is going to go back to loop and run again and again, and it's going to run 8 times because we gave the LDX value to be 8. So it's going to decrement by 1 each time it runs, and then when it's 0, it exits the loops and go to this jump to serial. Jump to the subroutine. That is serial hex2 that is doing this process, and then that is basically it. And we had to do the same thing here, but we had to do it twice because this is 16 bits. Here we did it for 8 bits. Okay, now let's go ahead and do that. So the logical left shift is not necessary, because when we are doing the addition, it automatically do the shifting by itself. So this part is not necessary. I'm going to do the other parts, loading, adding, and then decimal adjust accumulator and storing part. LDAA, and here we have to give two different names. Here we only name it as BZD, but here we have upper 4 bits and lower 4 bits, so we have to use two different names. So the high byte I'm using BZD plus 1. I write the explanation here. Load the high byte of BCD to ACCA. The next one, add carry to with itself, ADCA plus 1. And this one, add the high byte of the BCD to itself with carry. And then we use the DA, this decimal adjust accumulator A. It will adjust whatever the sum we get into BZD. It's only 0 to 9 range. It will bring to that range only. So decimal, it should be done after addition. We are dealing with binary addition. We have to do this. DA only comes after the addition process. So here we are using ADCA, so this DA comes after that. Decimal adjust accumulator A. STA BCD plus 1. On store the storing process, store the result back to the high byte of BCD. Okay, and then we have to do this one again. The previous one, if you look at this, we just did it once. Now we are doing it twice because of the 16 bits. So again, same thing, load into accumulator A. Now we are dealing with the low byte, so just name it as BCD, and then load the low byte of BCD into ACCA. And then ADCA, add carry to with itself, CD add the low byte of BCD to itself with carry. And DA for the decimal adjust accumulator A. And then STA on store the result back to the low byte of BCD. Okay, and that is basically it. And then as we did here, we had to do the decrement of X because this loop has to be running 16 times. So we have to do the decrement of x. That's the decrement of loop counter index x register. And we set BNE loop branch not equal to 0. So until this x value becomes 0, it's going to keep on running. So this one, branch if not equal to 0, repeat the loop. Okay, and then that is basically the thing. And then here, if you look at this, we are calling the serial hex 2, and then RTS is returned from subroutine. JSR serial jump to subroutine. So it's after this loop process done, it's gonna jump to subroutine, and then it's gonna do this. Okay, what does it do is it remember 8-bit values, shift the values 4 bits down. Okay, LSR. That's why we don't need the shift here, because this one does it for us. And then this one branch to the subroutine, that serial hex one that does this. What does it do is it turn off the higher order 4 bits in this one, and then override this, set this one into the ASCII range, and then all this stuff right here. Okay, so this is what happened, but we are interested in this right now because all the others are available for us already. We just have to deal with this one and complete this. And here we had to do this one twice because we have a higher byte and lower byte. This one only done once here because this one only have 8 bits, and that is just 1 byte, so we don't need to do twice. But here we are dealing with 16 bits, so we need to do this process twice, only this JSR serial hex2 part. So in order to make this one twice, we have to bring out the higher order byte and the lower order byte. So here, let's bring the lower order byte first. So that is LDAA, then BCD, this one, load the low byte BCD into ACC. Then now to branch to subroutine, to jump to subroutine, we put JSR and then serial hex2. That's what we want to jump. So we have to follow the exact same letter, that is first letter capital, serial x2. Okay, and then this is for the low order byte. Now this one jumping there. Call, what's happening here is call serial x2. Subroutine to print the least significant bit of the BCD value. And then we have to do the same thing for the higher byte as well, that is most significant bit. So LDAA BCD plus 1. What does this one do is load the high byte. of BCD to ACCA. Yes, our serial X2. For serial X2. Subroutine to print the MSB of the BCD value. Okay, so that's basically it. And then RTS is already returned from subroutine. Let's go ahead and run this one and see if it's working properly. Okay, I'm gonna reset everything. Reset, run. Okay, now I'm getting the values, and I want to make sure it's ending exactly at the same point. Okay, so it started from 9347 as I see. Started at 9347 and ending at 2005. And this is some error because if I reset and run, maybe it works properly. Because if I click the mouse here, it's gonna do some damage to this. So if I just run, I just will keep the mouse away, not touch it anymore. Okay, now it's exactly printing what we needed. We starting from 9347 and ended at 2005, and that's what we want to happen. We just successfully convert the given number into BCD.